Hello everyone, and today we're talking about energy, and it's a very easy thing to talk about, but it's not an easy concept to define. We all have an instinctive idea about what we think energy is, but in science we're looking to be a little bit more precise than that. So let's start off with our best current definitions of energy. Energy is the capacity to do work, but it comes in many different forms. There is a set amount of energy in the universe, and we cannot create any new energy, we can just change it into different forms, and this is what we call the first law of thermodynamics. Energy cannot be created or destroyed, it can only change form. There are, as we said, different types of energy, and we're going to go through most of the major ones here. There is kinetic energy, which is the energy that is due to the moving of objects with mass. There is potential energy, which is energy due to position or deformation, and that corresponds to gravitational or elastic potential energy. So if we're talking about when you put something up on a high shelf, it has the potential to fall to the floor under gravity, but the shelf is stopping it from doing so. And when you squeeze a rubber ball, it has the potential to bounce back to its normal shape, but it's not doing because your hand is still in it. There is also chemical energy, which is energy due to chemical bonds. So when chemical bonds change, that energy can be released or sucked in. Thermal energy is energy stored in the movement of molecules of a substance. So we're not talking about the movement of an object, we're talking about the energy carried by the molecules in that object. And then we have electrical energy, which is energy due to the movement of charged particles through a field. Then there's nuclear energy, which is found in the atomic nuclei between the nucleons, the protons and the neutrons. And this is different from chemical energy, it's in a different part of the atom, of the molecule. And finally, there's mass energy. Yes, mass energy. Even mass is just another form of energy. So when we start to get a little bit more formal in defining energy, we need to give it units, and the fundamental unit of energy is the joule. However, the joule can be derived from SI units in a number of ways, and here are many of the ways that the joule is defined as other units. It can be defined as a Newton meter, as a Pascal meter cubed, as a watt second, as a Coulomb volt, or as a kilogram meter per second squared. Just an additional note, you need to be careful when you're using Newton meters because this is also the unit of torque, a rotational force. And if you're in a rotational system, the amount of energy and the amount of Newton meters may not always be referring to the same thing. So energy, as we said, can change as well. They can occur in many different ways. It's chemical, physical, and whatever else. Finding new ways to control energy is what innovation in industry is all about. So we're focusing here on the energy of moving objects. That is our current topic, as we're following on from the laws of motion. However, there are many ways to control energy, and it's very simply controlling energy which allows us to do anything at all. So, do you know what energy is now? We've said in the past that work is a form of energy, and we've also said that energy is a capacity to do work. And this may sound a bit circular, and you might actually be confused on this point, but there isn't a great deal more to say. Everything in the universe, even mass, is energy. So all the objects in the universe, but also all the things that they are doing and all the ways that they are interacting, it's all energy. So everything is really just energy moving around somehow. So as we get a little bit deeper into looking at energy, we're going to move on to the second law of thermodynamics, which makes an even more important statement about the way energy behaves. Probably the easiest way to think about it is in terms of heat, but this second law applies to every different type of energy exchange. So Clausius, is the scientist who made this statement, says that heat can never pass from a colder to a warmer body without some other change connected therewith occurring at the same time. Slightly old language there, but basically he's saying heat will not go on its own from a colder body to a warmer body. You must use energy in order to move it there. That's what fridges do. They use energy to move all the heat out of your fridge so that it's cold inside. And this is true of all energy. It can never move from being spread out to being concentrated unless you spend some other energy to move it there. So what are the implications of the second law? Well, with our current understanding, the second law seems to be pointing to the end of the universe. So that's something to look forward to. So the second law states that energy cannot concentrate. You will always spend more energy somewhere else. So if energy cannot concentrate, it can only spread out. And this is true in all reactions. In any closed system, energy is always more spread out after a reaction than before it. And this is what is known as entropy. So let's talk a little more about entropy. Entropy is often defined something along the lines of the amount of disorder in a system. It's important not to get this confused with just chaos, because entropy is a precise value that can be calculated in SI units. And one of the rules is entropy always increases in a closed system. And the universe, as far as we know, is a closed system, so the eventual outcome is that all the energy in the universe will spread out as much as it can be spread out, and there will be no fuel left for any changes to occur. There will be the minimum possible amount of energy in every part of the universe, and that will be as far as energy can spread out. And there are various theories for why this might happen or might not happen, or what might happen after that. But at this point, it's really unknown what this long-term end of the universe theory will be. What we call this model is the heat death of the universe. So that's something nice to look forward to as well. So we'll just finish our first part on energy there, and in the next part we're going to look at a couple of specific forms of energy in simple models. Bye for now.